Shropshire Council has embarked on a programme known as the Primary Capital Programme, or PCP, which will result in the amalgamation of existing infants and junior schools to provide single, unified primary schools. Gaia is assisting the Council to ensure that its commitments to sustainable development are met throughout all stages of the PCP, through avoidance of waste to conserve resources, improving building performance to reduce carbon emissions, optimising natural resources such as daylight and air movement for ventilation, to deliver best value and create good conditions for teaching and learning, and to avoid conditions in products, chemicals and off-gassing materials that may be toxic to minimise health risks. An audit of building performance was carried out on Mereside School in Shrewsbury, which was formed from the merged Holy Cross and Springfield schools. This would clarify how the building worked and would be used for future reference, identifying improvements and how these could be made in accordance with best value. The audit comprised an airtightness test, thermal imaging, daylight estimation and dust mite sampling. It took place on the 16th and 17th of February 2010. Lighting is fundamental to the way teachers and children experience the school environment and how they're able to respond to certain tasks. Buildings should use daylight as much as possible, as long as it doesn't create disruption. Small amounts of daylight may be inadequate to prevent the use of artificial lights. There will be amenity benefits, but energy and cost savings will not be achieved. Then again, too much daylight often means too much heat and glare. For comfort and energy efficiency, good control is essential. It was evident from visits to Shropshire PCP schools that current daylighting is mixed, with good and poor examples. In the Holy Cross building, peak solar gain from the south is resisted, but there is potentially a lot of daylight. Where necessary, roof lights provide light to the back of the room. But in a number of classrooms, too much solar ingress is caused by too much glazing, and the roof lights were found to be not sufficiently translucent. There's a risk of glare problems in the afternoon, and fans and artificial cooling may be required. Recommendations to address these include designing structural overhangs or deciduous planting, or both, to cut out peak sun, improving lighting efficiency and controls, and raising awareness amongst staff and pupils. Dust mites are known to contribute to health-related problems and to accumulate in fabrics, carpets and furnishings. There's an increasing aspiration to design out the environments that they can exist in, from houses and schools. An area still to be determined is the specification of flooring materials, and Gaia proposed investigating the presence of dust mites. From the multitude of textile objects, those which are actually contaminated with house dust mites and should be subsequently treated can be determined with the Acarex test. The test is a dipstick test, which indicates the contamination by house dust mites in dust samples with a colour reaction. These dust samples are obtained separately from each textile object with the help of a vacuum cleaner and the Acared fine particle collector. The overall contamination was low, in line with the reputation of the school as one of the cleanest in the region. However, tests in other schools should be made and, where necessary, guidance given on cleaning regimes and finishes. Defective insulation and leaks are a major source of inefficiency in contemporary buildings, and defects in a building's thermal insulation and airtightness do not only create excessive energy demand and running costs, they also create the condition for a poor indoor climate. Thermography is used to study temperature variations over the surface of a structure. Variations in the structure's thermal resistance can be observed. Leakage of cold or warm air through the structure also affects the surface temperature, meaning that insulation defects, thermal bridges and air leaks in a building can be located. Before dawn, once the building had been brought up to temperature, thermal imaging of the building fabric was undertaken to identify and record areas of weakness. There were specific areas of moisture ingress which not only lead to deterioration but are also a potential source of mould and moisture and building-related ill health. The report indicates a number of specific areas of leakage that require remediation and in some cases further investigation. When they were built, buildings such as Mereside School were not subject to the same standards of energy efficiency that are required today. Even the poor regulatory standards were sometimes treated casually and may not have been met in practice. Over time, the poor fabric performance is likely to deteriorate due to movement, moisture ingress, failure of components such as windows and doors, and interventions for maintenance such as painting. The test set out to depressurise and test for leaks, then pressurise to establish air permeability of the area, to fill the area with smoke, and then pressurise and observe leakage. The airtightness tests identified very major weaknesses in the fabric. Substantial air leakage was found associated with the windows and doors and through the ceiling voids in all 3 areas. Leakage was found around single-glazed steel-framed windows in the first building, and around some of the double-glazed UPVC windows in sample areas 2 and 3, where the draft seals had clearly failed. Leakage also affected the eaves, roof parapet areas and wall panels. A section of Holy Cross tested at 18.4 air changes per hour at 50 pascals. Hence, we would expect for the heat to escape in less than 4 minutes with a 20-mile-an-hour wind. It is vital for future comfort and energy efficiency that the air tightness remediation takes place.